Hold up your hand. Look at it. There is a number associated with that hand, the amount of information it carries. Every position of every atom, every spin of every electron, every quantum field that gives it shape, a staggering number. But here is what physicists in the 1970s started to suspect, that information is not really inside your hand. It is printed on a surface around you, a two-dimensional surface. This is not metaphor, this is not a thought experiment, this is what the math actually says. And by the end of this video, you will understand exactly why. The idea is called the holographic principle, and at its heart sits one simple, audacious equation. The Bekenstein-Hawking entropy formula, S equals K times A, divided by 4 times the Planck length squared. Let us unpack what each piece means. S is entropy, a measure of how much information is hidden in a system. K is Boltzmann's constant, the bridge between thermodynamics and probability. A is the surface area of the boundary enclosing the region. And the Planck length is the smallest meaningful unit of distance in our universe, about 1.6 times 10 to the minus 35 meters. Now plug in the numbers for a black hole the mass of our Sun. Its event horizon has a radius of just 3 kilometers. Its surface area about 113 square kilometers. Run that through the formula and you get a number, staggeringly large, almost incomprehensible. 10 to the 77th, 10 followed by 77 zeros. That is how many bits of information a sun-mass black hole stores. And every single one of them lives on its surface, not inside, on the boundary. You might be wondering, who cares about black holes? Why is this idea worth your attention? Because the holographic principle is not just about black holes. It has reshaped 3 of the deepest problems in modern physics. First, the black hole information paradox. When matter falls in, where does its quantum state go? Second, quantum gravity. How do you reconcile general relativity with quantum mechanics? And third, perhaps the strangest of all, whether reality itself is some kind of computation projected from a lower dimensional surface. One idea, 3 frontiers. Here is the chain that connects them. In 1972, Jacob Bekenstein was a young physicist with a quiet but radical question. If you throw a book into a black hole, where does its information go? Quantum mechanics has a sacred rule: information can never be destroyed. But a black hole seems to swallow it forever. Bekenstein's insight was to look at entropy. He proved that when matter falls into a black hole, the entropy does not disappear. It gets stored, and not just stored, but stored in proportion to the area of the event horizon, not its volume. This is the moment that broke physics, because every other system in nature stores information in its volume. A box twice as big can hold roughly 8 times as much, but a black hole stores information by area. Twice as big means only 4 times as much. 2 years later, Stephen Hawking made it precise. Every quarter of a Planck area squared on the event horizon stores exactly 1 bit of information. That is the formula we just saw. The surface, not the interior, holds the data. And this was the first hint of something deeper, something almost too strange to believe. In 1993, the Dutch physicist Gerard 't Hooft asked the next obvious question. What if this is not just a fact about black holes? What if it is true for every region of space? Take any volume, a box, a star, even your own body. The maximum information it can contain is bounded by its surface area, divided by 4 Planck lengths squared. Information less than or equal to area, divided by 4 L Planck squared. That is the bound. Reality, it seems, has less room than it looks like it does. 2 years later, Susskind made the idea explicit and gave it the name we use today. The holographic principle. The universe behaves like a hologram, 3 dimensions encoded in 2. Then came the bombshell. In 1997, a young Argentine physicist at Princeton named Juan Maldacena published a 53-page paper that would become the most cited paper in theoretical physics history. He did not just theorize the holographic principle, he proved a specific, exact version of it. Take a 5-dimensional space called anti-de Sitter space. Put quantum gravity inside it. Now look at the 4-dimensional boundary. Maldacena showed that a quantum field theory Living on that boundary describes the same physics, exactly the same physics, as the gravity inside. Two completely different mathematical frameworks, two different numbers of dimensions. One identical universe. He called it the ADS-CFT correspondence. 20,000 citations later, it remains the cleanest evidence we have that the holographic principle is real. 5 physicists, 25 years, one idea that quietly remade modern physics. Bekenstein gave us the entropy, Hawking gave us the formula. De Hooft generalized it, Susskind named it, Maldacena proved it. And the work continues today. In holographic entanglement entropy, in quantum error correction, in the structure of the universe, in the conjectured equivalence between wormholes and entangled particles. Every one of those frontiers traces back to a single observation, that the inside might just be a projection of the boundary. So here is where we land. The universe might have less information than you think, less depth than your eyes suggest. The information that defines you, this room, this entire planet, all of it could be encoded on a distant surface, projected inward like the most exquisite hologram ever conceived. The universe has no inside. It writes itself on its surface. If this idea fascinated you, you will love the next one. What happens when these same physicists try to use the holographic principle to understand your own brain? I will see you there.